everybody, and welcome to the Learn It, Turn It, Burn It Torque and Drag mini-series, episode number 2. Today is going to be another awesome episode. Thank you guys so much for being here. Today's episode is brought to you by Friction Tools. So happy to have these guys be a part of the show and be a part of this. This is going to be an absolutely amazing event. I hope everybody's got their pen and pad ready to be able to take a lot of notes. We're going to be educating you guys on so much torque and drag stuff. I'm really excited about this. This is absolutely fantastic. Last week, we had Brandon Foster on here. We had over 300 and something people watching in real time. It was absolutely barn burner of an episode. If you have not seen it, you can go back and watch it here on LinkedIn. Even though it's a little bit harder to find like old stuff on LinkedIn, we will make a featured link or something on my LinkedIn profile to be able to make it easier. So you can go back and watch it on LinkedIn and be able to see all of the comments that came in from everybody. Or you can go back and watch it on YouTube, where you will also be able to see some comments, not all of the comments, but you'll be able to see some of them there. It's a little bit easier to find on YouTube. So it's YouTube, just search Gibson Reports or Vidor Locksmith, and you'll find your way over to the site. Once again, today is brought to you by Friction Tools. Huge shout out to those guys. Thank you so much for being a part of this. All right. So yeah, last week we had Brandon Foster came on and did the introduction to the series, which was absolutely fantastic. This week, we've got Truls Larsen talking about ancillary applications, and it's going to be great stuff. Next week, we've got Dr. C from OU coming on to be able to teach us about basic physics. That one, we're going to be talking about low side torque and drag, capstan effect, reaming vectors, and how the models work. So be sure that everybody, if you've got any questions, fire them off during the presentation as we're going along. That will make things go a lot easier towards the end. Because as we're going through, I'll be watching, taking notes, and starring all the questions, and then we'll go back through and be able to ask all of those questions in order at the end with rules. So, yeah. So, guys, let me know where you're watching from. Please put us a little comment into the comment section now. Let us know where you guys are watching from. Really happy to be able to have you guys be a part of this. So we'll give everybody a shout out here in a minute. Also, want to be able to tell you this. If you are wanting to be able to make sure that you get notified of when we do the shows, here's this. So if you go over to my profile, there is a little notification icon. If you click that, then you will be sure to be notified when we go live, right? Or, and also probably helps, click the follow button. Either one of those will be able to help make sure that you are getting updated when the content is becoming available, right? So do that. Follow myself, follow our guests, follow the companies that are sponsoring. Speaking of which, put that back up there. There we go. All right. This is really cool. I don't know if you guys saw, some of y'all saw the Vidor Locksmith show from the other day, but this is the first time this has ever happened. The guys over at Friction Tools did something really cool. They actually sent me samples of their product, right? This is the disruptor here, right? It's pretty big. There you go. You guys get a look of it. This is the actual thing. They sent me. He was like, let's get your address and we'll send you something over. And I was like, okay, that sounds like a good idea, right? I just thought it was going to be a model. No, they sent me full-size disruptors. I don't really have anything to disrupt, so maybe giving these away. I don't know. Might just put them on the shelves back there. But huge thanks to Ken over at Friction Tools for sending these over to us. I mean, granted, I didn't have these but 5 minutes, and my significant other was already asking if she could have them. And she didn't know what they were. She just wanted them for herself. So, I don't know. We'll make a coffee table or something out of them like that. So, since they are the sponsor for today's show, do me a favor in the comment section. Oh, I should probably do this. Let's say hi to everybody first. All right, so we got David tuning in from Houston. Thanks for being here. Juan from, or it doesn't say where he's from. He says Buenos Dias. Jose say good morning. Sadiq tuning in from Dubai. Alfredo from the Woodlands. Mr. John DeWart tuning in from Colorado. Jose Vaca tuning in from Las Colinas. Chris Webb tuning in from San Antonio. Hello from the banks of the Buffalo Bayou in Houston. George, thanks for being here. We do appreciate it. George Towell, Denmark, Calgary, Conroe. All right, tuning in from Dubai. I tried to send him a bit once. It didn't work out. It got sent back to me. I'm going to try that again. Today, tuning in from Malaysia. Florida, tuning in from Austria. Wow, we've got an international audience go today. Somebody tuned in from Austin. Thanks for being here and being close. Once again, Jose from Mexico, Houston, China. Woo, Saudi Arabia for Ahmed. Thanks for guys for being here. Andre for tuning in from Norway. He's part of the Oliasoft team. Thanks for being here. Dean tuning in from Edmonton. Andrew Switzer tuning in from Midland. Thanks for being here. And Paul Moore back out the same direction. He's in Stanton. I know that one. Sorry, I'm getting emails here. They're getting in the way. Dr. C, who's going to be on the show next week. All right. And then Shriek tuning in from Pakistan. I don't know. Got through most of these. Let's finish them out. Robert from Netherlands. Felipe from Brazil. Oliasoft team is tuning in from Oslo. Thanks for being here. And Azar from India. Thank you, guys. I went through all those pretty quick. All right. Once again, if you guys want to keep giving us shout outs here on the screen, please continue to do so. All right. Let me clean up the bottom edge of this drill bit real quick. But if you guys want to win a drill bit, this one's purple and gold. Right? You guys want to win yourself a drill bit? Do this for me. Brand. Type in hashtag friction tools, and you will get to win yourself a drill bit. Life-size one of these big ones. Probably not downhole worthy, but really cool something to be able to take to the beach, put on your desk, conversation starter at the office, whatever it may be. Brought to you by Friction Tools. And speaking of these guys, let us share. We've got a nice little clip from them. Watch this, and we'll be right back with you.
Friction Tool Solutions has developed and patented an industry first, the Disruptor, a centralizer designed to exploit the negative energy of hole drag by turning side contact force into applied casing oscillation, effectively providing dynamic friction values when sliding your casing. We have successfully deployed over 125,000 disruptors, and the proven, repeatable benefits delivered to our clients include a significant increase in available hook load throughout the entire lateral section, mitigates the need to rotate casing, and the disruptor saves valuable rig time with consistent, improved run speed averages. Now available in 15 countries and expanding. The Disruptor. Engage and disrupt friction.
All right, there we go. Special thanks there once again to the guys at Friction Tools for being a part of today's show and bringing you today's presentation. So let me do this. Let me add this to the screen. We've got 51. I'll let that keep going for a little bit, right? Maybe we'll just stop Lars like part of the way through his presentation and then do the drawing because I can still see a lot of comments coming in. Let me see here. Yeah, they're still racking up. All right. Guys, here's what we'll do. Truls, I'm going to bring you on, and then what we'll do is we'll start part of the way through, whenever we feel like having like a quick little intermittent break, and then we'll do the drawing. Get some more people involved. All right. Truls, thank you so much for being here, sir.
Thank you. That's been looking forward to it.
Well, give us just a quick background on who you are and what you're going to be talking about today.
Yeah, so I've got a PhD in nuclear physics, and after I finished that one, I've been working with the oil industry for, it's about 14 years now. So my first 10 years there were with FMC Technologies, where I basically worked with subsea sensors of the more complex kind, multi-phase flow meters and leak detectors and such. And then 4 years ago, I started working for Oliasoft, and been enjoying that a lot, and have been working on basically on drilling mechanics calculations since I started here. And that, of course, ties nicely into what I'm going to talk about, the ancillary applications of any torque and drag analysis.
Excellent. Well, like I said to the audience earlier, please just put in hashtag friction tools to be able to win your chance at winning a bit and maybe even one of these disruptors. As well as like, share, subscribe. Maybe even if you would please tag a friend in the comment section. Let them know that this event is going on right now and it is live. Yes, you can go back and watch it afterwards, but if you want to tag somebody right now and then bring them over to be able to join in and watch. All right, Jules, I'll go ahead and add, if you'll go ahead and pull up your presentation, I'll add everything in there so that you can. There we go. We'll add that in. And there we go.
Yeah. So I'll just start then.
Yeah, go ahead.
Yeah, thanks.
The show is yours, sir.
Yeah. So we got the logo for Friction. So I'll be switching over to the next presentation, or to my other presentation. But so this basically is what we're going to talk about today. To talk about the ancillary applications. Basically, what does it mean? Well, it's about what you can do with the results that you get from torque and drag analysis. Because of course you can use the results as is, look at the hook loads like Brandon talked about last week, and the torques, etc., how to actually get to your TD. But you can also use all the result you or some of the results that you get from that analysis to do other types of analysis. And what the first thing we're going to look at is the side force, which obviously is one of the main output parameters from any torque and drag analysis. And then we're going to look at how we can use that parameter to do wear calculations. We're going to look a little bit on how standoff devices affects wear. And then we're going to do a little bit about stretch and twist and a little bit about stress at the end. Of course, stretch and twist also really ties into the other main parameters of any torque and drag calculations, which is the tension and the torque. So it would have been really nice if the audience had the presentations from Stefan Menand that will be in 2 weeks' time, but I guess we got at least a little bit of an introduction last week from Brandon. So we shouldn't be that far off to start to look at this. So let me switch to the other one. I had to fix a couple of things. That's why we are changing here. So first thing, the side force. So you do your torque and drag analysis, and you get the side force out. But of course, before you actually do the torque and drag analysis, you have to choose a model, right? That was also mentioned by Brandon. That there are we have the classic soft string developed in the early 80s by Johansik and collaborators. And we also in later times we've gotten the stiff string, because obviously the drill string is not just a heavy piece of spaghetti lying at the bottom of the hole. It's stiff. It bends. You have to apply forces to bend it, and this is basically what stiff string tries to do. What I also mentioned here is that there are other more advanced soft string models, but basically they are still soft string models, but they compared to the Johansik one, they are so-called two-dimensional or three-dimensional analysis, while the classic Johansik one is one-dimensional. But you need to sort of choose what sort of model you want to use. So one can, of course, look at the well in question and look at the dog legs, and as is most commonly known, stiff string plays an important role when you do have dog legs that are, say, in the area of 15 to 20 degrees per 100 feet. But when the dog legs are less than that, it's not that it doesn't necessarily give you a more accurate results, right? But anyhow, we're not going to discuss which model to use. We're just going to say that you have chosen your model, and of course, once you've chosen the model, there is basically two things that can be done in the model. It can calculate the drag, say the tension in the string, from as a function of the side force, or the side force can be calculated as a function of the drag, so that the model would either calculate the drag first and then the side force, or it would calculate the side force first and then calculate the drag. So it's, in a way, one might think that well, it doesn't really matter, but on a detailed level, it could play play a minor role. So of course, that's one of the things that comes into consideration when one wants to get a good side force for our wear calculations that we will look at later. So one other thing that is also important to choose, that's whether to run effective tension or a true tension analysis. It was briefly mentioned a week ago, and I think most probably that Stefan will mention this in much more detail. But simply said, effective tension is basically to look at all the piston forces acting on a piece of segment. Let's say that this is a drill pipe with a connector at the bottom and at the top, and oh well, usually there's not that one at the bottom and at the top. The one at the bottom here would belong to the next drill pipe below it. But so the effective tension would basically look at all the forces on this and then calculate the sum of all those forces, keeping in mind that these forces, they are vector forces, and then the resulting sum would be the tension that you apply to the drill string. So if you go with different type of models called the true tension, you would basically let all forces act upon this drill pipe, and you would calculate one at a time and take them into consideration for calculating the tension. So basically, if you put something, or if there is a piston force at the bottom of the pipe, and there is a continuous wall of steel going much higher up into the well, the pressure at the low side will obviously be lower than the pressure at the high side, so that the pressure from the mud, basically. So that would actually give you a different type of localized tension, but of course the sum of it all would be the same. So basically, you should, in most cases, you shouldn't end up with the same sort of hook load if you choose effective or true tension. So piston effects, then, that I mentioned that, so they also come into play here, of course, when we try to figure out what the side force is. So it's a pressure effect. Obviously, that pressure effect can be static, or it could be dynamic. So if you're tripping in and you're not pumping anything, just running the drill string into the hole, you get some pressure effects. But once you start pumping, you get different effects. Obviously, the viscous mud is flowing in the annulus. That, of course, also affects the tension, which then will affect the side force. Of course, this type of friction parameters you insert into your analysis will have a big impact on the side force that you calculate, and the viscous friction. So if you're pumping and the mud is moving, the viscosity will pull on the drill string in the direction of the flow. Obviously, one might think that if you are pumping, well, the flow is moving down on the inside, it's moving up on the outside. But then keep in mind that the surface area, the cross-sectional surface area of the drill pipe, is smaller than the outside. So there will be a net effect in the upward direction if you're pumping down in a standard way. And of course, if you apply rotation to your operation, then that also has a huge effect the side force. So in this presentation, I'll mostly use these two trajectories, and the main reason is that the left one, it's a surveyed trajectory, so it has a survey station at about every 100 feet. And the trajectory on our right-hand side is a parametric one, so it's totally smooth. It uses the standard trajectory models for calculating a smooth path from between two points, basically, in the well. So I'll refer to them as the surveyed one or the parametric one, and of course they have. It's not that easy to see on the left-hand side here, but you can see that there is a casing going all the way down here. There's a liner going down here, and there's a casing going from this point, says target 3 here, all the way up to top side. So we talked about that the side force depends on what sort of model you use. But of course, it also depends on the geometry of the well. So, and basically, one could look at the azimuthal and the inclination as two separate parameters, and one can use those separately, and that's typically what's used in the Johansic model. But it's easier to plot these things as doglegs, because then you see the overall severity of how much you are turning or building or dropping off. So when you choose the classic soft string model, there is one assumption that's kind of important to keep in the back of your mind, and that's to derive their formula. Johansic and company, they actually had to do one approximation, and that was to say that, well, if our angles, our turning or building or dropping off angles are small, then we approximate that sinus, the alpha, is equal to alpha, to the angle. So of course, then we know that, and then obviously there are other approximations that often must be done to other models. And if you choose a different model, it can be important sometimes to know what sort of approximation it uses, and so you can make a good choice with the well that you want to analyze. So, of course, high dogleg versus low dogleg. So we can see on our left-hand side here, that's our parametric well. It's basically it's a straight, it's a vertical. It starts with a vertical section going down to 1,800 feet or so, and then there is a section with a dogleg of 3 degrees per 100 feet. Then there is another sail off and another dogleg at 3, and so on all the way down. So it only has sort of abrupt changes in the doglegs, and if not, it's just smooth sail off. But then if you look on the right hand side, this is a proper measured parametric well. So here we can see that even though this obviously at some point was a parametric well, once it was drilled, of course, it's always impossible to replicate what you do on a software, in a software or in a planning phase. And we can see here that the doglegs, they are jumping back and forth. It's basically, we see sort of perhaps tortuosity, but also general, you try to steer as well as possible. And it looks like here that they've done a reasonably good job. The changes aren't that big, about a degree per 100 feet, and apart from a small section down at 9,000 feet, where we suddenly see a big jump in the doglegs going all the way up to 8 degrees. So quite a lot more than our parametric well, which doesn't have more than 3. But still, we're going to look at how these doglegs and how they actually shift, how actually that affects our side forces, and thus also affect our ancillary analysis. So the side force obviously is a function of time, right? So as you move the drill string into the hole or out of the hole for that matter, you move it, and of course the position it's located at will give you different side forces, right? So the tip, the drill bit, if it's a drill string you're running down, then if it's at the just at the casing shoe of the last section and starting its drilling, it will have different side forces compared to if it's all the way at the bottom where you're going to stop drilling at your TD. So it's also right, as we saw on the previous slide, that the side force also depends on the parameter, if it's parametric or surveyed. Well, of course, it depends a lot of if you're moving in or out, and that we can actually see here on the plot on the right side, because here I plotted the side force versus the measured depth. So this is how the side forces on the drill string looks like when we have reached 19,500 feet, I think. So our yellow line, it's the tripping inside forces. And of course, we can see in the beginning it's vertical, so there is nothing, and then we have a little bit of a value, and then it sort of follows the other operations. We can see that the tripping out, the red one, gives a much higher side force, and especially actually at the highest point in the well where there actually is some dog legs. Of course, if we start rotating, as was mentioned earlier, rotation, basically you're moving the friction into torque. The drag friction is moved into the torque component, and thus the side forces, if you're back reaming, you get lower side forces. And here you can see that it actually drops by quite a lot. Actually, it's getting much closer to the tripping in side forces than it is to the tripping out. And of course, if one tries to study this a little bit more, you can realize that, of course, here we are close to vertical. Our parametric well here has just started to do a little bit of a build. So in this section and in this section, we are actually tension dominated. So the side force here in these areas comes more or less purely from the tension, and there is a very small component of the weight that actually contributes to the side force. But of course, as we are getting further down into the well, the tension, of course, drops as you're getting closer and closer to the bottom. And of course, then the tension starts to have a magnitude which is similar to the weight of a component, and it can even go below. Thus, this lower section, it's basically weight dominated. And you can also see that because it doesn't matter whether or not you're moving in or you're moving out, the side force there is just the same. And of course, this is a sail-off section, and this last portion is a sail-off section. And this was basically our last section where we did a little bit of a build, I think, or it was a drop-off. One other thing to keep in mind is, of course, that since it is a function of time, if you're just moving down with a constant velocity, of course, you can perhaps predict the side forces a little bit more easily. But if you're trying to clean the hole because you realize that you're starting to get the cuttings bad and you're reciprocating back and forth and pumping, and you're standing there for several hours, of course, this will change the side forces. You will basically, if you're rotating, you'll jump between the yellow one and the blue one. If you're not rotating, just moving up and down, you'll have side forces going from 40 pounds per feet up to close to 200. So it has a huge impact what actually you are doing. So if you, in this case, had been rotating, of course, the side forces wouldn't have increased that much, especially in this area. And looking at the side forces here, might give us an indication that this is a place in the well where we most probably will see more wear compared to the lower section of the well. So, but what we can also see from this parametric well is that the side forces, they have a very smooth development. I mean, we don't see any spikes anywhere. I mean, of course, there's a jump when we start having a dog leg, and we have a jump back down when we're going to a sail-off section. But it's basically a feature that's important to know about, that these parametric wells, the side forces are very smooth. So let's take a look at how it actually looks for our surveyed well, because here obviously we would expect the side forces to be very different. So we can see that there is, similar to the parametric well, that there is, if we sort of I've done the same 3 types of analysis there. I've been back reaming, I've been tripping in, I've now been tripping out. So 1 with rotation and 2 other operations in and out without rotation. So we can basically see the same here, that the areas that are tension dominated, that's the areas where we have a huge difference between tripping out and tripping in. And we can see that at the bottom here, they are almost all of them lying on top of each other. So this would be a weight dominated area, while this upper part of the well and even the middle part of the well, you can see there are big fluctuations between the tripping out and the tripping in. So this is tension dominated areas. And of course, what's really worth noticing is that we have big local fluctuations. And if you remember back to the 2 wells that I showed you, the surveyed well was it's not really a vertical well, but it builds up to something like 30 degrees, while the other one builds up to an inclination of about 80 degrees. So this is a rather vertical well, but still it behaves like this. You get all these fluctuations, and you also get high side forces in these types of wells. Same as you would get if you build different if you are going into a more lateral well. So let's see. I mentioned that the side force is a time dependent variable. So basically what I've done here is I'm comparing the side force when I'm at different locations, just to illustrate that actually the side force changes by quite a lot as you move down into the well. So the red dots here, they represent the side forces when the drill string has reached the casing shoe, while the blue one shows the results, the side forces, when the drill string is located at 13,500 feet. And of course, we can move it all the way down to the bottom, and especially pay close attention to actually what happens at the lowest side here, what will actually happen to the side forces here. So here you can actually see that we had an area just below the casing shoe where actually the side forces were higher when we were halfway down, and they actually dropped off as we got closer to the bottom of this well. So it might not always be that easy to predict how the side forces will come out. So having done a good job before you actually start looking at it, having done good choices, selected good friction factors, good tooling, etc., and good model, then you can start doing the analysis, and don't be surprised if things doesn't necessarily show up as the same way as you might intuitively think, especially on surveyed trajectories. So that's what I wanted to say about the side force, and now we can actually start using the side force for something that we actually need. So we have a well, and of course, at some point in time, there might be a request for drilling maybe some kickoff wells or doing something to increase the oil recovery, because the original well might have dropped its production by quite a lot. But if you've done many operations to actually build that well, then you have to take into consideration that, well, can we actually do more operations without losing the integrity of the casing that we have installed? And that's where wear analysis comes in, right? Because you cannot wear the walls of the casings more than what actually the casing analysis tells you is the maximum. So the ones responsible for the casing strength calculations, they will actually tell you what the minimum wall thickness can be to maintain the integrity of the well. And then, of course, if you are the one responsible for doing the torque and drag analysis, you might be the one that has to start looking at wear and to see what these new operations might actually mean to the integrity of the well that we want to do more operations in. So wear, it's pure and simple, it's caused by friction, right? So if you had a perfect lubricant, there wouldn't be any wear. Or alternatively, if you had a standoff device with some friction reduction tooling on it, ball bearings or rod bearings or something, then of course the friction gets reduced, and of course that also reduces the wear on the casing. But obviously, full drill string will never have this. There will be quite a lot of friction in many places. Thus, we have to figure out where and how this friction actually is causing the wear. So obviously, if we are obviously sliding down into the well, but we of course have the choice to rotate, and if we do choose to rotate during an operation, well, we know that these two velocity vectors, they are perpendicular to each other, right? So if you take a standard rotation frequency, which would be 120 RPM, what would actually that compare to sliding wise? So if we do this example with a 5-inch drill pipe and you're rotating it at 120 RPMs, that would actually correspond to a velocity of the outer diameter of 157 feet per minute. And that would basically be the same as sliding in a full stand in 40 seconds, which is quite fast. So when it comes to wear, which of course depends on how things are moving and how long they are moving, we need to keep in mind that the rotation velocity is, for all practical cases, a lot higher than the sliding velocity. And in many cases, like if you're drilling, it will be enormously much bigger, and it would be basically the rotation that's causing your wear. Now, the wear formula is probably one of the simpler things that you can actually do in drilling mechanics. It's as simple as the side force times the length the component you're looking at moves. And this was presented, I think, also in the ASTs by Hall. I'm not sure about the exact year, but it could have been Bradley as well. But you can read about a little bit more about actually how this was presented in papers by these two. So they came up with this wear formula, and they said that the wear volume is equal to a constant that they called the wear factor, and then multiply that with the side force and the length you are moving the component that you want to calculate the wear for. The wear factor is given as 1 over pressure. So it's a factor that you need to sort of either have found through maybe some studies of previous analysis, or from surveys or tests in labs, etc. So on a typical basis, it's maybe around in the order of magnitude, it's like 10 to the minus 10th per psi, but that's an order of magnitude. So that would be about 10 to minus 14 pascals if you're doing SI units. Now, the side force we've talked a lot about, of course. So let's dig a little bit into this this movement parameter, the L move. So it's a function of both the sliding and the rotational motion. So obviously we're either moving down or we're moving up, but we're also rotating, right? So we figured out that, of course, that the rotation velocity is a lot higher than the sliding velocity. So this L move isn't the same as moving this piece of pipe, say its own length down, which would be say 30 feet. It's going to be minimum 30 feet. If you're rotating, it's going to be a lot longer. So we'll look a little bit about into that. But what's worth noticing is that there is no dependence on the contact cross section. As you can see from the formula, there is no cross section that goes into this one. So even though if there is a groove that's already worn into the casing and you're doing a new operation, you have obviously, if the size of the drill pipe that you're running in is the same as the previous time, it'll fit nicely into the groove. But even though it now has a bigger contact area because it now is a groove there compared to the sort of the first run of a drill pipe, you're still wearing out the same volume. But obviously we're talking about a volume, right? We're not yet talking about how deep the groove actually is. But there is one caveat, and that's if you do have rotation, the contact cross section does come into play here. And of course, we want to also figure out a little bit about the wear location, because obviously if you're running a soft string model, all your grooves will be located at the low side of the well. But if your model is a bit more sophisticated, it could tell you something about actually where the grooves end up. And they might not end up in the same place if you are on a moving in operation, a trip in operation, compared to a trip out operation. So just a little example on how we actually can figure out this movement length. So if we take our previous example with a rotation of 120 RPM and a tripping speed of 30 feet per minute, well, if we calculate the total length, this will move. So we'll move this one down, then one stand, we get to a totally different L move value compared to the 30 meters that we would not 30 feet that we would have gotten if we were not rotating. So you can see here how much this oh sorry, we're not moving one stand, we're moving it down for 1 minute. Yep. So 160 feet compared to only 30, that's quite a lot more, which of course gives you a much bigger wear factor, wear volume value. So of course, if you want to, you can do a little bit of an exercise and try to see, okay, so if you're just rotating, how much slower would I have to rotate if the wear caused by only rotation were to be the same as the one caused by only sliding, and that you would have to reduce the rotation velocity down to 40 RPMs. But then you of course have to take into consideration that if you are reducing the rotation frequency, then of course you are changing the torque and drag analysis, and then your side force changes And then it's not that obvious if actually reducing the rotation frequency will give you less wear. And so we might, of course, also have standoff devices added to our drill string, or maybe we're running a liner, for instance. In most cases, you wouldn't perhaps not do this if you were running a casing, because that would basically be the last operation that you would see on that casing, as it would be covered by a new casing after the new casing is installed. So let's say that you are running a liner, and obviously you do want it centralized in the hole, so you can get a good cementing job and have a good control of how the forces actually will, the static forces will act on the liner. So of course, standoff devices, they have a bigger outer diameter. That means that if we remember back to our little example, of course, that the diameter goes into the calculation of the rotation velocity. So obviously that increases, and that would thus increase our movement. So if we do use standoff devices, that could have an increased effect on the wear. But of course, if there are friction reducing elements on this standoff device, well then it might give you a lot less wear, because you might get into a situation where this would be if you could rotate it in, you would be the same as just a sliding operation. So if it was equipped with friction reducing elements, both in the sliding axial direction and also in the rotational direction, obviously there would be no wear for that component at all. So there are some benefits, but there are some things that one also needs to keep in mind, that it will have an impact on the wear of the casing. So now the next important part is actually, we have now basically looked at how we can calculate wear on a small piece of a component. And obviously we have several hundreds of them, right, to reach our depth, to reach our TD. And we need to accumulate all of these small segments that we have calculated the wear on. Right? So we have to do, first of all, we have to do a local accumulation. So this, on the right-hand side, you see a cross-section where I've tried to illustrate a piece of casing as orange here. And here we see that there are two worn grooves, gray and blue, marked A and B. And what we need to figure out is, to get these sort of grooves located here, we have to figure out where in the HLA coordinate system these grooves are located. And if we have a model that supports calculating the local position of the drill string, we can start figuring out where the new grooves actually end up. And of course, as we move down, the tension in the string and the side forces changes. So the drill string could move around, obviously, as we are moving down into the well. So you could have a wear as well up here in the beginning, and as you get further down, you might get into compression in this area of the string, and then it moves over to the other side, and then starts to causing wear on the other side of the casing. So what's important here to notice is that, okay, so you can try to figure out where it is, but you also need to try to figure out how should you actually accumulate the wear. So you calculated the wear volume for one section, you've done your analysis, and you found the depth, and then you basically have two choices, right? You can do some binning in azimuth or along here to see, okay, so if the drill string ends up between, say, the beginning of the blue half moon here and the end here, then we know that we need to add the new wear, we need to add this to the B groove, right? Or it could end up on the other side and we need to add it to the A groove. But if we have a binning that doesn't really correspond to the grooves that we are creating, then suddenly we might start splitting one groove into two grooves, right? So if the bin limit was located directly here where it's touching, and then at one point the model calculated the value where it ended up on the left side, it would go into the left side bin, and then a bit further down it might move just a couple of degrees over onto the other side of the bin limit, and then it would start adding wear to call it the B side here. And then in reality, that might not be the case, right? Because it just moved a degree or two, and most likely it will just be the same groove. So you can, if you have local azimuthal binning, end up with actually getting the wrong wear. One groove could actually be split into two, but also it could be vice versa. Like two grooves could be merged into one. So if you get a bit of wear just on the inside of the limit on one side of the bin, and then get a little bit of wear just on the right side of the other side of the bin, then those two grooves would also be combined into one, even though they would be two separate grooves. Right? So if there is some a priori binning in the type of analysis that you do, you need to keep an eye on this, because this can cause you to not get the right groove depths. Of course, there is more to wear accumulation. We're not just accumulating at the cross section. We are also accumulating as we are moving down, so in the axial direction. So we know that the side force changes with time, right? So we calculate the side force basically at discrete points in time, or at discrete MD points. And that's basically what I'm trying to illustrate here on the right-hand side. So I've said that for this little illustration, that the resolution of my casing, so that's these squares here that you see like a ladder going down. So if I do get wear on one of these segments, then obviously I have to apply that to the entire segment. So if there is a side force and the movement on this segment, I have to apply it here. So what I'm basically illustrating is that if you try to follow one of the colored connectors, we can see actually when the connector is moving fully across a segment that's defined by the resolution of the analysis, and when it only partially moves across. So if it follow the yellow one here, we can see it starts on the inside, so it will not be fully worn. We get some reds in sometimes, but many of these movements, these small movements that this drill string does not cause a full movement across it, right? But every time we move it, right, we recalculate the side force. So the side force continuously changes. So basically, the groove the wear groove does not have the same depth across the entire segment in reality. But when we do analysis, that's what we do, right? So we're going to take a little bit of look into how that actually can affect some of our results. So back to the parametric trajectory. So on the right hand side, so just to recap, we have the dog legs on the left side here, and on the right hand side we see a wear groove analysis, where we've actually plotted the groove depth as a percentage of the wall thickness of the casing. So for this chart here, I've did a drilling from the casing shoe, the red line here, located at about 16,500 and down to 19,500, I think. And then I did a remount. And this I did with sort of forcing the classic Johansik equations for torque and drag, and I applied. I should say I applied not the realistic wear constant here, because obviously it's just two operations, and you can see it's at 30%. So I think I multiplied the wear factor here with about 1,000 to get some values that are not 0.000, etc. Just for illustrational purposes. But what you can see here is that the groove depth has accumulated to something that's like 3.5 times as much at the top, maybe as we expected when we looked at the side force, and we can also see that there is a little bit of wiggle in the results, right? These small wiggles, they actually come from the choice I did in my analysis here, right? So they do not necessarily represent the reality. So some of these wiggles aren't really there in reality. They are just an artifact of simulation resolution, because we are doing discrete point analysis. So let's take a look at our survey and let's take a closer look at this resolution of the casing, right? So what we're looking at here on the right hand side is a blue line, which has a casing as a resolution of the casing analysis, casing wear analysis of 100 feet. So basically, I've segmented the casing into 100 feet segments, and then run the analysis. And then I did the same analysis over again, where I segmented it into 1 feet. And looking at this plot, it doesn't really look that bad, does it? I mean, it seems to be following, the blue seems to be following the red quite well. But if we zoom a little bit in here, we can actually see something quite interesting. So here we've zoomed into an area where we actually had quite high wear. Here I think I've actually ran it with more the proper parameters, and here you can see that the small drilling operation and the reaming out actually doesn't cause much wear. We were like at 0.01 inch. So you need to do several operations actually to actually get some wear that is significant. But what we're look at here is the difference, right? So the blue points being the 100-meter resolution, and one might think that it doesn't look that bad, but then at this 2,000 feet location, we actually get a lot less wear than we do just by changing the resolution of the analysis. And that should cause a cause for notice, right? That this is an important factor actually to take into consideration when you do this type of analysis. Most analysis, of course, goes a lot faster, especially wear analysis goes a lot faster if you do with coarser resolution. But what you get out might actually not be the truth. What you can also see has happened here is that we have basically a spike here with the 1 feet resolution, while it actually drops off with 100 feet resolution. And what's interesting or if we try to analyze this situation a little bit, the reason we actually see this is that between these two, basically, in this case, these two survey stations, right? There could be a lot more changes in the doglegs than we actually anticipate. And the wear here would just be distributed all over. And we have a discretely calculated side force, which also basically gets smeared out over a bigger area. And that's actually what's causing this difference just by choice of resolution. So let's take a look at actually how how the wear grooves look like cross-sectional wise. So going back to the parametric well, where we look at classic soft string torque and drag analysis with all the grooves located at the low side. So we just assume that the drill string is heavy spaghetti, right? So the drill string would have been lying here and causing this groove. This was run with an exaggerated wear factor. So as you see here on the right hand side, we're at what 30% something. So we're located at 2,200 feet. Yeah, so we're at here. So we're so at around 30%, and it says here it's 30%. So okay, let's look at how it looks further down. So obviously the groove is still located at the bottom. We're now at 15,200, so we are getting close, very close to the end of our casing. But it's still located at bottom, and everything has accumulated there. So it's a wear. The wear groove is here in this location is 10%. So look what happens. Let's see now what happens if we do take a more dynamic approach to figuring out where the wear grooves actually are. So if we try to calculate where the wear grooves are, or if we let our torque and drag model calculate the location of the drill string, we can also then place the wear at the correct location. And if the wear location can be placed more correctly, we can start actually getting a wear analysis that actually gives us better information. And the information is there, right? I mean, calculating the location of a drill string at a certain point is basically just looking at the tension vector at the bottom and at the top of a segment. And that will actually tell you the location of, and then combine that with the gravity, and then you can actually figure out where the drill string ends up inside the casing. It might not be 100% correct. It might not be as correct as if you were doing a stiff string analysis. If you have good control of all parameters on a stiff string analysis, it might tell you a bit, maybe quite a lot more. But it does give in many cases, will give you a very good indication of where the strings are ending up inside the casing. So here we see it ends up at the top side, and we can also see that actually the groove is slightly smaller, and there appears to be actually one additional groove here located somewhere. It's 0.1%, so it's probably invisible on this this chart. Let's look at the other point that we looked at earlier, the one that was close to the end of the liner. And here we see a dramatic change. So what we had before, we had one groove and it was about 10%. So now we have gotten a maximum groove here, which is 8.5. And there seem to be a lot of other grooves located on the left-hand side there. As you can see, there is a small change in color. I hope this is visible. So we can do a zoom in and try to look at it and see if we can see it a bit better. And you can see that we have one big continuous groove. It's not located all the way at the bottom. It's slightly on the left side. And there are other smaller grooves located here that are a bit further up on the, call it the slope on the side. So we actually, by using more information from the torque and drag analysis, we can actually get a more accurate maximum wear groove depth. And in this case, it changed by 1.5%, which basically is a bit. So you don't necessarily want to be too conservative when you do wear analysis, because you are basically, sorry about that. Yep. So you don't want to be too conservative because you don't want to tell the management that, well, we can't do more operations here because we have to be on the conservative side. So I guess we have to shut the well down. the management will hope that you actually do a really good job at this and actually come back and say, well, I think this could be possible if we follow this plan. Then we might be within the acceptable limits for the wear of the casing. And basically that concludes our wear section. I don't know if David said he wanted to cut me off at some point, but I guess he'll break in if it's needed. If not, we'll continue on with.
Keep going. Keep going. You're doing just fine. We'll do the drawing at the end.
Yeah.
Make sure everybody's actually tuning in.
Yeah. So now let's take a small look at what actually these standoff devices actually does with the wear. So obviously they have there is a plethora of standoff devices, right? From rigid ones that you can mount onto the normal piece of pipe, to the ones that are part of the of a component, call it a standoff device that is just basically the same as a drill pipe, but with its own standoff wings. Of course, you have bowstrings, etc. And the wings, they can be, they can be straight, but they can also be curved. And there are different ways of fitting them, and they might move on the string. They might not move on the drill string. And what you need. What's needed to take into consideration is that if you are running these down, right, they will affect the wear grooves in a very different way compared to running a normal drill string. Right, so if they have obviously if they have a small radius, or not obviously necessarily, but the groove depth increases a lot faster with time. And if they have a big radius, the groove depth will actually increase slower with time, if you take into consideration that they are affected by the same or calculated with the same side force and the same move length. So are we doing it with rotation or without rotation? And is there actual or is there rotational friction reduction in question here, right? So if we take a look on the illustration on the right-hand side, right here, the fins, they look rather narrow. So obviously if they were tripping this one in and the side forces were high, obviously they would quicker create a bigger groove. But obviously at some point, if it's as big as this, then you might start getting a distribution of the side forces onto more than one fin, and it is a much more complicated analysis to do it, but it could be necessary in cases where you are close to the limit of your wall thickness. Right? So another case that's also important to look at is wireline. So if you want to run instrumentation into your hole, of course these are maybe similar, right, in diameter as our previous casing, standoff wings. The wireline is very small. Obviously, it's not that heavy in itself. It might not have that much heavy components hanging at the bottom, but since it's small, it will quicker create a deeper groove. So basically, I've put up a bit of geometric considerations that you could do, and if you take a look at this later on, you can try to convince yourself that obviously this isn't solvable analytically. This is basically a x plus sinus x situation, and that does not have an analytic solution. So when you do these types of analysis, you need to take that into consideration, that it is a bit tricky to figure out what it is, but what you should end up with is a bit of an understanding on how the wear volume, which I denoted here as the groove, because we're just looking at the cross section, right? So we're basically taking it as the derivative axial wise of the wear volume, so we get an area for the groove, and this has a relation to the depth, and it goes basically like this, and it actually will tell you that this small diameter wire, even though the side forces aren't that high on this one, will actually can also quickly create a small little groove and reduce the wall thickness maybe faster than you think. But of course, take into consideration how many times do you need to run it. It's only once, or do you run it every now and then between operations, etc., etc. And then we are basically finished with the final pieces of the wear, or an overview of the wear analysis that we can do. And the next one is stretch and twist. I think in a way that you probably will get more information as we go down the line with the other presenters the coming weeks. Obviously, when we go into stretch and twist and into stress analysis, we start also to depend upon the tension calculation from the torque and drag analysis. And obviously, choice of model here plays an important role as well. But we can calculate it once we have a tension result. It's possible to get stretch and twist calculation. It's also possible to calculate the stress. So there is one thing that I didn't mention in the beginning, which was also supposed to be talked about today, which was fatigue analysis. But I think I've understood already that it would take way too much time to do that, and I think fatigue analysis probably ties well in with stiff string modeling, which typically is a finite element analysis where vibration is something that is highly related, a highly related analysis. So hopefully we can hear something about that sort of analysis by Stefan Menon in 2 weeks' time. So let's dig into the stretch and twist analysis. So basically, it isn't that difficult, of course, to visualize stretch. Well, you have an element and you pull it at each side. Obviously, if it's a bit pliant, then it'll get longer, and if you push on each side, then it'll become a bit shorter. And twist is basically to rotate the same pliant element, rotate it one way at the bottom, or hold it steady at the bottom and rotate it at the top, and you get this twist into the element. And so we can of course do that with any sort of drill string, because obviously it's made of steel, and even though it might seem that pretty hard, it's still pliant enough. There is a yield limit basically where you can actually twist steel or compress it or stretch it, where it will act as a spring and just go back to its original geometric shape. So stretch, of course, it's part of the tension analysis. Obviously, then frictional drag comes into play here. And for the twist part, it's the rotational friction that comes into play. So on the stretch part, obviously, it's the axial friction from the sliding motion. And of course, again, the friction, it acts in the direction, or the friction force acts in the direction of the sum of the velocity vectors, right? So then one might think that, well, if we don't have any friction, and we can't have any twist, maybe we'll have some gravitational stretch, maybe. But let's take a look. Could there be more? Well, if we look at stretch, it is actually a bit more than that. It's actually a function of obviously, as we said, the tension, but it is also a function of the temperature, right? Because if you heat something up, it will typically expand. And pressure might actually cause your pipe to balloon, or I mean, it could also compress, right? If the pressure in the annulus is higher than the pressure inside the pipe, but in but in most cases, the pressure inside the pipe will either be the same as in the annulus, in the case of not pumping any mud at all, or in the cases where we actually are pumping, the pressure inside the pipe will be higher than inside the annulus. And of course, that will cause a ballooning effect. It will actually, I mean, exaggerated look like a balloon, right? There is actually a small illustration a bit later, I think. But so these are the three components. So even though if we do not have any friction, okay, so our tension here, our tension contribution to the stretch would be 0, but we would still have changes to the length due to the pressure and to the temperature, right? And then we were talking about the change in temperature from the top side, right? From before you put it into the hole. And obviously it can be hot, very hot as you get really deep. But if you do a little bit of an analysis of these formulas, you will see that in most cases you will be highly dominated by the tension, the delta temperature, right? The change in temperature from top side to whatever depth you are looking at will be small compared to any tension value. The same goes a bit with the pressure here, because we are looking at the pressure difference between the inside and the outside, not the absolute pressure. So let's then see how actually what sort of stretch would we get in this survey well that we've been using. So here on the right hand side, I've basically plotted a trip in, a trip out, but then I've also plotted 2 other interesting parameters here, right? Which is not that common perhaps. And if you are familiar with roadmap plots, this should look very familiar, right? And basically what I've done is I've taken the minimum hook load values, and I've calculated the stretch for those minimum hook load values. And then I've done the same with the maximum overpull. And then I've just calculated the stretch from the maximum overpull. So basically using the information on the yield of the components, and then figured out this yellow line, right? Obviously, when we were tripping in, the stretch is lower than when tripping out, and these 2 ones, they fall nicely in between, and we can see that the tripping out actually for this so I ran this analysis from about 15,000 feet. So what we see is the drill bit depth. So we are actually every point here on this line represent an accumulated stretch value. So when we are at 15,000 feet, the total stretch when we start to pull it out is 18, 19 feet. And obviously when we're tripping in, it's not that much. It's actually gotten a bit longer there as well. But what it is interesting to notice is that actually if you have to operate, or if you want to operate closer to your minimum hook load line, so basically the minimum hook load line, right? If you are familiar with this is related to buckling. So basically how low can you go on the hook load before your drill string goes to buckling somewhere in the hole. So here you can actually see that when we are at the bottom, if you would dare go very close to the minimum cloud line, the drill string actually would be shortened by, in this case, about 2.5, 3 feet, I think. So let's take a look at the stretch of our parametric well. So the previous well, right, it's sort of vertical, though it builds out to about 30 degrees, if I remember correctly. And this one, the parametric one, going out to about much more lateral, out to 80 degrees. Also, I think it's slightly longer, but not that much. They're similar in length. So I basically did the same thing here, but I've added also, now that we used it, so we see the stretch actually for the minimum hook load here as this purple line, and with the maximum overpull stretch here. And you can see that this actually, you can pull this string quite far before it actually breaks. So you can also actually take this information out from this sort of plot, right? So if you think you're stuck, you could, just as well as looking at the hook load, you could also measure how much pipe you've pulled out of the hole before you actually will reach the yield point of the drill pipe somewhere. So for this analysis, or this drill string that I used here, this could have been pulled as much as 24 feet actually if it was stuck at the bottom, without the bottom actually moving at all. But if we're just we're not stuck at all, and we're just running a normal trip out, in this case at some velocity, perhaps if I remember correctly, about 50 feet per minute or something, or was it 30? We actually have to pull it 20 feet before the bottom actually starts to move. So if we let's say we drill down to the bottom, and then when you start pulling out, you will have to pull 20 feet out before it actually starts to move at the bottom. And obviously that's pretty important to keep in mind if you plan to clean the hole before you actually start pulling the drill string out, right? If you know that it will take some hours, right, before all the cuttings is removed from the hole, or as much cuttings as you can hope for. If you want to reciprocate while doing this pumping operation, then obviously you probably should move the drill string more than 20 feet if you actually want to have some movement down by the drill bit. So in that sense, this is quite an important parameter to take into consideration. If you pull it less than 20 feet in this case, the bottom part of the drill string will not move at all. It will just be standing still, and you'll just elongate the remaining part of the drill string. Yeah. So what I also plotted here is how you can see how the stretch actually looks like when you are drilling. So here I applied just a standard drilling operation, and also showed how actually the stretch is affected if you would go to a maximum weight on bit. So there is not that much difference in this case. So we're probably running this analysis with a reasonably high weight on the bit, but you can see how it actually changes. And the green one is the tripping in line. So I tripped in here with a bit of different velocities. Sorry for those who can't see the difference between green and red here, but so the left one is the tripping in, and the red one on the right side is the drilling. So let's see how twists. No. We had one more. That's right. So obviously these are the accumulated values, right? So we have the drill bit depth. That's what we've been looking at. So once the bit reaches all these points, we know what the stretch is. But let's just take a little look at a snapshot, basically. So how actually does it look like? So we can look at it at two different points in the well. So we take the parametric well here, and we look at the point just below the casing shoe. So I skipped a couple of lines here to make it a little bit more clear, but we can see that both the tripping in and the drilling line here, they lie pretty close to each other. So I probably ran this down here to this point. Oh, it's actually slightly below. So yeah, so here we actually add a little bit of weight on the bit actually, but it doesn't really affect the stretch that much. It's, of course, it's more or less close to zero, and we are getting stretch. We're not getting stretch in the drill string before we actually get into a more vertical part of the well. And actually, you can see that the maximum wob line that I showed in the previous plot actually exhibit a high amount of compression, right? It actually is in compression all the way up to 2,000 feet, and actually the drill string has gotten nearly 2 feet shorter from the bottom up to 8,000 feet. But then, of course, it starts to become longer again. So, and then at the end you end up actually with a slightly positive value. And then if you do the same, look at the same when you're at the bottom, you can see also that the values, they shift up and you get more stretch as you get closer to the bottom. And obviously here you can see this 20 feet value that we saw as the lowest point on this tripping out line, telling you that, well, you want to reciprocate, you should pull more than 20 feet if you want to have some movement down by the bit. And then we can take a look at twist. So let's take a look at the survey well, because it exhibits a little bit more interesting features. So the twist formula is a lot simpler. It's just basically one equation. We had 3 equations, right, for the stretch, but for the twist we only have 1 equation. So torque obviously plays in the role in there, the length of the element that we're looking at, and then it's basically geometric and material parameters that goes into this equation. Right? So this J is the second moment of area, you have the Young's modulus, and you have the Poisson's ratio that goes into this equation. So basically what I did here is to basically show the same thing as what we did on the previous charts. We have this back ring operation, we have a trip in, out of here, and neutral weight, since now we're rotating, right? Compared to the other ones where we were not rotating, we were only looking at tripping operations without rotation. But of course here we can also take a look at the neutral weight, also called ROB, rotating off bottom. And I've also plotted the maximum torque twist line. So in most analysis, when you look at torque plots, you will have a maximum torque line as well. And from that line, you also can calculate the twist. So in this case, you can actually see how much you can twist the drill string, right? So this particular drill string that was used for this survey well had actually the possible. You can actually twist this at the maximum here at more than 250 degrees. But not when you reach the bottom, right? So the limiting location here seems to shift a little bit, probably depending on what sort of components are going through what sort of dog legs. So it's not the case always that these maximum lines are just increasing all the time. But what we can actually notice here, and was just a funny little coincidence, is that the trip out operation for actually this drill string that I used in this analysis, running that at 120 RPM would actually exceed the maximum torque twist. So obviously, if I looked at a torque plot, I'd seen this as well, but I was looking at twists. But the funny thing is that I could see the same thing here. Right? It actually gave me the same sort of information. So let's see if we can do something with that, because obviously I can't ream out I can't start reaming out. If that's the case, right, then I'll break the makeup torque on some other component. And right now I don't even know which component it is, but I can at least do the analysis over again and see if I can get it within the limits of the maximum torque. And here I've just reduced it, the rotation frequency to 100 RPMs, and then luckily I actually gotten below. So I could run it out here. I'm pretty close though to the limit, so I should probably be careful. But obviously, if you see such a thing, right, when you look at your torque and drag results, it would be nice actually to try to figure out which component is causing this, right? Because it's you would preferably you would want to move that maximum torque line further over to the right, or a maximum torque twist line, as it's called in this plot, since it's the twist we're looking at. So we could try to plot up the yield limiting depth. So the yield here is basically the makeup torque. So what we saw on the previous, or where we actually have gotten higher than the makeup torque. Look, it is located here at about 13,500 feet, I think. So if we look at this yield limiting plot, it basically shows us the limit in measured depth when the bit is at a different depth. So if you want to see where we have the limit, we need to find this 13,500, which is close to here, wasn't it? Look again, yes. So the limit was located here, and we can see that the limiting MD measured depth here is actually 0, right? So it's actually my last couple of components that I'm adding here. They actually have a weaker makeup torque. So those probably should be changed out to something different, or to something with a higher makeup torque, so that you can actually run with more with more room to spare for the rotation. So that concludes it for the twist and stretch and twist calculation, and what you can actually get from it. So we're now moving on to the last part, the stress calculations. Obviously, also a very important calculation when you think about casing design. But obviously, we don't want to break our drill pipes either. So we can do basically the exact same calculation for drill pipes. The main difference between doing stress calculation on drill pipes compared to casings is that we are actually in movement, right? We are moving the drill string, so we have both a longitudinal velocity, but we also have a rotational velocity that comes into play. We have torque, so those are extra parameters that we need to extra stresses that we need to take into consideration when we calculate the stress. So at least in my my gut feeling for stress is that it's not always that easy to understand what it actually is. So I actually tried to boil it down to something that might be a little bit more understandable. So I found a quote on Wikipedia that said that forces parallel and normal to the boundary of a small element, that's what stress is. And so I looked at it and thought, I don't think I fully get it. So I thought, well, I probably should have some images here. Maybe that might be a bit more helpful. So I think it does, especially when you look at all these different motions, right? Because they are not that easy to just remember, right? So obviously we have the same thing as we looked at with tension, and with stretch. We have the tension compression stuff, but we also have this shear forces that can act on an element, right? And the point here is that they're parallel to the surface where you are calculating the stress. So the parallel meanings basically, so if this red arrow is the force vector, Then the surface area you are looking at the stress, calculating the stress, is this light blue square at the top here. And we also have bending stress and transverse stress. Transverse shear stress, actually. So the bending is normal and the transverse shear is parallel. And you can do the same, basically sort of thought experiment, and then you can figure out how it actually works. So bending right normal, so that must be related to the surface along this curved line here, and at the backside where we can't see, or this side where we can see it here. And the transverse shear is actually then what's happening in a cross section on this rod. Torsional is a little bit more easy to understand. That looks very similar to the twist that we were looking at on the previous slides. And of course, ballooning. That's that I mentioned on the stretch calculation. Here is an illustration of how it actually looks like. So if you do have higher pressure on the inside compared to the outside, the walls will start to ballooning. And obviously it could be the opposite way in some cases. Well, I just came to mind a case where this can happen if you're running a string into the hole, and obviously in most cases you're not just continuously filling the drill string. You'll just fill it at certain intervals. Say you run it 1,000 feet or 2,000 feet, and then you fill it up to the top side, and then you run another 2,000 feet of pipe. Of course, in those cases, you will have pieces of pipe that are submerged in mud, but where there is actually air on the inside, and then you get into these scenarios where the walls here will actually be compressed. So how can we use this to actually calculate stress? Because this was a lot of different parameters. So what one actually does is actually to take all these stresses and combine them into one parameter, and that parameter is called von Mises stress, after obviously a mathematician and physicist who was called von Mises. And what you want to do is to actually find the so-called von Mises yield curve, where the stress is at its highest, has its highest value, right? So on a piece of drill pipe, there are basically two curves or two surfaces. So there is an inside, a smaller radius inside, and a bigger radius outside. So we need to actually try to figure out which one is the highest, and use the highest one when we compare it to the yield strength of the material, because that's what you actually want to do at the end. You want to see whether or not the von Mises calculated value exceeds the yield strength of the material that you are using. Because if you do, if it does, then it could break during an operation. So you should look at this, of course, before you start running anything into the hole, and make sure that what you plan to do doesn't break the drill string. So the von Mises stress is basically in a way it's a vector sum, squared square root of a vector sum. So it gets out as an absolute value, yeah. What we use it for, of course, is for simulation. You use it to calculate a maximum hook load. Of course, if you pull harder on the hook than the maximum hook load, then you know that somewhere in the hole the drill string will break. And of course, operationally, that it limits how much you actually want to pull. I mean, you set it hopefully with a good percentage lower, so no catastrophe happens. And this is basically as dry as it gets from Mises equations. So we have the different terms that gets into the calculation. So if we remember back to the illustration, the blue boxes that was stretched and bent and compressed. So we have the axial stress. We have something then called also called bending stress. Obviously, that's something that comes from the axial stress as you go through a curvature in the well geometrically. Of course, it can buckle. That induces a huge amount of extra stress. But of course, that's something you should avoid at all costs, so that you don't get stuck, can't get further down. The torsional stress, of course, related to the torque, and then we have the ones related to the delta pressure, which is the radial and the hoop stress, and we have the transverse shear stress, right? So all of these have more or less straight formulas. They depend on this parameter that I've listed here, and then you combine them like this in this rather long equation, and you end up with a von Mises stress. So what's important to notice is that some of these actually stresses that you calculate, they have a sign, and some of them actually work in opposite direction, so that they cancel out. That is a feature of how all these stresses actually work together. Some of them might actually sometimes cancel out. So let's just take a small look at the end. So this is my last slide. How stress actually look like for pulling out the hole with rotation, because then here we can actually see a little bit about how the magnitude of these different stresses are. So we also can see that on the left hand side here we have some negative stresses. In this case, it's the hoop stress, and I think it's the radial stress here. In this case, they are negative, and all the other ones are either very close to zero or just above zero. That being the bending stress and the buckling stress. Of course, in this operation, I didn't run into buckling, so that should be zero. And also the transverse shear stress here is also very, very small. The bending stress being the biggest one of those that are close to zero. And you can also see that the bending stress, obviously in a parametric well, it only has a value in these regions where we do have a dogleg. So the ones that actually contribute to the von Mises stress, which is the green line furthermost to the right, it is these two blue lines, which is the torsional and the axial stress. So they are the main contributors to the von Mises stress. And on the far right hand side there, we see our limit. So with this setup I had here, this is a setup that should be fine to run into the hole. With this setup, we are below, at least by 30-35% below the yield strength of the pipe, drill pipes. Then we can do the same thing with the survey trajectory, and obviously you see here, like we looked at the red line on the left hand side, that the bending stress only has a value when there is doglegs. Obviously, the doglegs here are distributed all over, and they're fluctuating back and forth since it is a survey well. So here it actually is a contribution more or less everywhere throughout the well. But even with this this surveyed well, where we saw that there was in the region where we had doglegs up to 8 degrees, which I think, if I remember correctly, is located here. They're still a lot smaller. The bending stresses are still a lot smaller compared to the axial stress, the blue this blue line, and the torsional stress is the light blue line. And then we also can see here that the von Mises stress is the sum of them all, and of course always will lie on the right side, and also for this case even further from the yield strength of this drill string. So I think with that, spent a fair amount of time. I'd just like to say thank you for giving me the the opportunity to present.
Well, Jules, thank you so much for presenting. Oops, wrong button. Again, wrong button. There we go. All right. For anybody who didn't think that we weren't going to get real deep and technical, well, they were sadly mistaken. We got deep and technical on this one. If you guys have questions, now it is time for Q&A. So once again, much thanks to Friction Tool Solutions for being the sponsor for this episode. I've got highlighted a whole bunch of questions that go pretty far back. I think we'll block those. All right. That went pretty far back, and we still need to do the giveaway. So we'll do the giveaway real quick while it gives everybody a chance to be able to add in any questions that they have, and then we'll start going through them. Once again, guys, please like, share, subscribe, tag a friend in the comment section. If you learned anything out of this today, anything, just tag somebody else, share it, do something like that. This is what allows me to be able the opportunity to be able to keep doing this for you guys. Instead of y'all having to pay $25,000 and begging your boss to be able to sign off on, going and doing some classes or something. Even just a like or a comment helps be able to push this over to just that next level. All right, so let's add this to the stream. Here we go. We've had 75 people enter in for the drawing, and there we go. Let's see who today's winner is. Hopefully it's not me like we did last week on the Vidor Locksmith show, but we'll see here. David Thill. David, I know exactly what he wants, and it's sitting right over there. I already moved it off. He wants the giant LSU bit. So, David, thank you for watching the show, sir. I do appreciate it. We will get that over to you shortly. We've already got a couple of things lined up to send him. All right, so we'll take that one off. All right, Truls, here we go. Just before we get started, we'll have a couple of people who said, great presentation. Thank you. Eric, you've got your question in here, or your comment. You asked a question earlier in the show, but for some reason it didn't pop up on this side. I saw it on LinkedIn, but it didn't pop up on this side. So if you would ask that question again, so we make sure that we get it in here. All right, so I'm gonna take that one off. Hunter says, thank you for the presentation. Appreciate y'all. Archer says, thank you, Truls. Thank you for sharing this info. We appreciate the space to have these conversations in. All right, I'm going to start to highlight some of these other questions and comments in here so that we don't miss addressing them. All right, so now I'm going to jump over to the start side of this. And the first one came in. It said, hello, piston force due to what? Jar? Question mark. It's all we got to think about at the very beginning. So these came in from...
yeah. Yes. So, I mean, piston forces, right? What we're talking about in that case is hydraulics, right? Hydrostatic pressure, right? So imagine you took a tubing, a piece of pipe, and you closed off the end and pushed it into whatever liquid. The further you pushed it down, you would experience two things, right? Of course, it would be buoyant, right, since the inside is filled with air. But if what you're actually putting in is weak, then it would actually buckle. And why would it buckle? Well, it buckles because there is a force at the tip of what you actually, the pipe that you put in. So it's basically the hydrostatic force, and it could be hydrodynamic, it could be fluids moving as well, right? It doesn't really matter, but there is a pressure there. And as long as the pressure acts on a surface, that's a force. There could be a pressure on an opposing surface, right? Of course, that could be very close by, so it wouldn't actually, the forces wouldn't sort of accumulate upwards into your drill string. But it's basically, that's basically it. I mean, if there is a continuous sort of section of steel that goes, that force is transmitted along that material.
All right. Next one we've got Jose Mark says, I assume hydraulic lift. I really wish I had context or the timestamp was what you said to be able to say in reference to this, but
Seemed like was related to the previous question, I think. Yeah, hydraulic lift, of
I
course. I
think they
mean,
were close.
yeah. So I mean, it's of course, I mean, buoyancy, right? I mean, it can reduce your side forces, right? Because you get less tension. But of course, you could be in a location where this, call it hydraulic lift, this buoyancy, right, actually contributes to compression in the string, which in many cases would increase the side forces. So you would basically need to dig into the details. Where is what's causing this or that, and looking at looking at something like buoyancy, right, on a general basis. Well, you would have to look at it on a special case. So we're looking at this piece of component located at that location, subjected to this side of these types of forces and this type of geometry, and that's how you actually can understand what actually is going on.
All right. Now, if I remember correctly, I don't remember exactly where the question came in, but I know it was early in here. So Eric did have the question: what conditions cause drill pipe to sides, move sides of the well from high side to low side?
Yeah, so you can take the most basic example, right? So you start drilling vertically down, and then you start to build, right? Increase the angle, the inclination, and of course, once you've drilled down to whatever, let's say that you do 5,000 feet vertical, and then you start building, and you do that for a couple of thousand feet, right? This might not be that obvious since you are drilling where you would be lying, but let's take then the simple case. Let's say that you are pulling out, right? Obviously, the topmost part of the pipe will be in the vertical section, will be in tension, and it will then pull through the bend. It will pull on the lower part, so it will lift itself up, right? Because the one vector has an inclination, the other force vector is vertical, and if you take the sum of those, well, that's pointing perpendicular to the way you are building, right? So it will lift into the top side when you're pulling out. If you're running it down, well, then it depends, right? It could be lying on the top side while you are tripping in. But if you get into the case where actually the weight or the compression or the tension is low enough, it could fall down to the lower side. Gravity would take hold of it and move it down. Obviously, you could have scenarios where you drop off. Of course, you'd lie on the low side, maybe in most of the cases, but it all depends on the geometry actually that's further down and what's behind you. And obviously, if you look at that tension plot line, you will in many cases, right, when you're moving in, you will see that you have a neutral point. There is a point on the drill string where the tension is zero.
All right. Well, let's move on. Here we got the next one. Cody says, "Are you able to take into account in your modeling the difference between more flexible leading joint of casing?"
I mean, it's if something is flexible, right? I mean, that's a good question. I think it ties a bit into, I mean, soft string versus stiff string choice. Because if something is flexible, it's a soft string, right? Basically, you shouldn't include a soft flexible joint into into an analysis of stress, for instance, right? Because what's the stress? It's difficult to say, right? If it's jointed, obviously it bends without basically any forces apart from the weight, right? Or if it's oiled properly. I think, I mean, if it's something is flexible, I think that would be something that you basically wouldn't see something like that have an effect on a soft string in a soft string model. Running it with a stiff string model, it basically would the stiff string model would basically treat it as a soft string in that area, right? It wouldn't just behave like a soft string in that area.
All right. Next one here. Let me unhard that one. Cody, what's essentially the reduction in end loading / buckling it would provide, especially in large casing diameters?
I'm not sure what he is after. Do you remember where that was?
I can't remember right off. Cody, if you're still watching, you got some more questions, so just throw it back out to us.
Maybe it was related to where. No, yeah.
I don't know. Maybe it might have been comment with somebody else in the comment section. We'll keep going. Can casing smooth micro dog legs and build sections in a well for lower peak side force when drilling subsequent sections?
Obviously, I mean, as Brandon mentioned last week, right? I mean, some micro dog legs, right? If you're running up and down, running the drill string up and down, some of these micro dog legs actually sort of gets worn out, right? Of course, we're talking about the open hole section, right? Obviously, and if it doesn't, I don't think it really matters if these micro dog legs exist in a constant dog leg section, or if they're in just a sail off section, right? I mean, there's weight, there's forces. You are the same way as you do wear calculation on a casing, right? I mean, obviously you do get wear on an open hole as well, right? So you do get, as he mentioned as well, right? I mean, you don't see the same friction factors used when you're going in or out, right? I mean, it's there are lots of microstructure, right, that gets smoothed out as you are running more and more components past them, right? And as it gets smoother, does the friction factors change across during the operation? They're not constant even during the operation.
All right, well, there we go. Next one here. Are the calculated points at set distances or calculated at or at calculated contact points? Sorry, if I could learn how to read, maybe this show would go a lot smoother.
No, I think that was totally understandable. No, I mean, it's obviously, I mean, you need to contact now and calculate or well, to say it in a different way, you need to apply the calculated side force or whatever force you're calculating, or stress, or you need to calculate it at a point of interest, right? So in the middle of a drill pipe, it will be hanging in the air all of the time, right? Or in the mud all of the time, right? It won't be touching anything unless it's subjected to an extreme dog leg with a high degree of tension, right? Didn't mention something in the presentation, but it was mentioned a week back about this bending stress magnification factor. This thing that basically it's pushing it. I mean, it's straightening the middle part of a bent pipe. So the actual angle, the bending angle close to the connector is actually a lot bigger than the geometric average one between the two pipes. So this, I mean, calculate things at points of importance. That's extremely important. The points of interest is that's where you have to apply all the calculation, right? Apply them at the point. So if it's a contact point, like a tool joint, then of course that's where it should be applied. That's where it should be calculated as well.
All right, next one here. This is from Adrian. Can you elaborate on the piston effect and its effect on side force calculations?
Yeah, well, it's it on a general basis, right? If you do use piston effects, that's basically doing a true tension analysis. Now we haven't in this series we haven't gone into depth of the difference between true tension and effective tension, but on a general basis, it shouldn't give you that much of a different hook load result, right? When you sum everything up, everything, right, from bottom to top. So you can take all the small forces coming from mechanical to hydrostatic to hydrodynamic, take all those small forces, add them to your calculation, and then sum it all up at the end. Or if you take a small portion, you sum them, take another small portion, you sum them, and you do that way, etc. You should end up with the same thing, right? The hook load shouldn't change, right? But obviously, if you do all the little ones one at a time and look at them, obviously, if you do use true tension, it will change the way the side force plot looks. So you could actually, by choosing one or the other, get two different side force charts, but you still getting the same thing. Exactly, right? And that's a choice, right? In all software that I know of, I mean, you choose it, right? You do one or the other, right? And you have to, perhaps, if you want to be thorough, why not do one of each and look at them? Look at the side forces. You want to do a wear calculation, so that's important, right? You, of course, if you're doing a drilling, want to create a roadmap, of course, it doesn't matter that much. I mean, the hook load is basically the same for both of them, right? Of course, the limit maps might look different. So the minimum hook load, the maximum minimum hook load might be different if you use a true tension compared to an effective tension. But they shouldn't differ that much in the sense of an operational issue. But you would see, and you should expect, a little bit of difference.
All right, let's jump into the next one. This is going to be a fun one. So Brian asks, how does the change in azimuth or turn rate at horizontal rotary drilling with RSS, flat turns, the horseshoe wells that Shell drilled, and for that fact, Chesapeake did, affect torque and drag? So essentially a U-turn in the lateral.
That's good question. So let's in terms of side forces, right? I mean, there has to be compression, obviously, because you are drilling. So obviously, if you're turning that way, then your drill string will move up onto the curb, like a racing car. Obviously, moves on the outside curve, so change, so turn, so change. So it's talking about the turn rate. So basically, we're talking about basically a dog leg here, where we're only talking about the azimuth. There is no change in inclination. As long as that one is basically constant, obviously, then you will have increasing side forces, right, as you move backwards, because the compression, as the further you get away from the drill bit, the more the compression increases. So the further you're away, but still in that build, you will get higher wear. So if you had say a liner going all the way into the beginning of this flat turn, then obviously that would probably see a lot of wear. But of course, I mean, you would have to, I mean, it's just from a general point of view, but of course, it depends on what the geometry looks on the upside, on the above it, and what's the weight of the components. How is it a very long, heavy, complex BHA, or is it something neat and light, or But what is it, right? I mean, you have to look at all the details. They all play together, and they changing something out with something else. It's totally different results, right? Totally different limitations on what you can do.
All right. So we've got a handful more questions here. Let's see here. Russell asks, won't the pipe get pulled to the same spot throughout initially, starting with one groove and just grow from there?
That's actually a very good question, right? I mean, if it, let's for the sake of discussion, right, say that you get two grooves, right? They're located close to one another, right? And then for some or other reason, there is a lot of build and turn. There's it's a real well. We're talking about in reality, right? Not just the simulation, right? So the grooves are lying here, and there are micro tortuosity. There's general, call it macroscopic tortuosity that you can see with the survey, and of course it moves a bit back and forth, right? So I can't see in any cases if, I mean, I would think that in most cases then it would grow and become one. It would two, and then you get one more in the middle. Then it starts to wear on one side, and then suddenly they are growing into one groove. Obviously, I think that's what's happened in reality. And if you have a good piece of software, it should basically be able to do the same thing, right? See if they actually start growing together, right? I mean, where are they? They shouldn't. If it's, does it rely on actually on binning, as it is the 360 degrees? Is it actually segmented into small bins, right? Or is it not? Is it dynamic? So small pieces of such a puzzle, right, might give you very different results, like we discussed in the presentation.
All right. So Ali, you're right. Thank you. No, he's not talking to me. Where is a function of total revolutions and side force? So lowering RPM does not always reduce the wear.
Exactly, right? Because we looked at it, right? We looked at the plot with the side force, where we did a trip in and a trip out, and one with reaming, and obviously it was lying between the trip out trip line. And obviously, if you change the tripping velocity and also change, or you could do one or the other, right, or both, and change the rotation speed, the rotation frequency, and obviously you change the side force, right? So you can lower the RPM, but you increase the side force. So you need to look at it, right? I mean, is it then again? And it's a very non-trivial functional dependence on these two, right? There is so much that goes into calculating the side force, right? You do the full-blown torque and drag analysis, and one of the parameters that you get out with everything else is the side force. So just changing one parameter, you change that, of course the length changes. It's not obvious what the end result will be if you actually gain something, or if you actually are causing more wear. I mean, it could even happen that you reduce the RPM and get more wear.
There we go. All right, Ali, thanks for your question. All right, Divine is here for a second week in a row, so we do appreciate that. How can I determine the recommended side load setting of my rotary steerable system for the long tangent sections of my extended reach well?
That's a question I can't answer. I do not have much knowledge on rotary steerable system. So sorry about that. Maybe
No
there's
worries.
someone at later time that can answer that question.
Well, Brandon Foster is going to come back for
Yeah.
for his second episode, the 8th episode in the entire series. So might be a question we hold off for him, or this might sound like you might need to hire somebody internally to help out with that. Is the minimum hook load stretch calculated and graphed with or without rotation?
So in this case, what I showed was a minimum hook load without rotation. Yes. So it was because you were looking at the stretch, and I thought we'll just do that simple, not have both stretch and twist at the same time in the plots. So that was just a pure minimum trip in hook load.
All right. This yield method is very helpful for tapered drill strings. Not a question, just a good comment. Figured to throw it out there. All right. Then we've got Florian, who's asking, at a casing where, what measurement tool and interpretation method do you prefer to calibrate wear models? Also considering that milling patterns should not be mixed up with wear.
Yeah, that's I haven't. Unfortunately, I haven't worked with this long enough to actually have much knowledge on calibration models and actually calibration aperture. But yeah, as he says, right? I mean, when you do this sort of calibrations, it's really important to have a very thorough understanding of the setup. I mean, I know that from working with instrumentation. Don't sort of bias your reading in any sort of direction. But no, I can't recommend anything specific. No, sorry.
Just going through there and showing a couple of the comments. So Brian said, thanks, David and Truls. Excellent show. Dallas says, a great presentation, and thank you. Thank you to both of you guys for watching. I do appreciate it. All right. So let's go on to the next one. So here's the questions for Brian. We are seeing more propped open float valve kickstand tripping in, which eliminates the pipe fills, but also eliminates any LWD surface testing. A little bit different there. I thought I saw a question mark in there, so sorry, my bad. Could you explain again how to calculate the azimuth or position in high side plane of each segment of drill string in soft string model? Now, just so everybody knows, let's see, where is it?
Yeah, there, I can hear you again.
There we go. So soft string versus stiff string will be January 30th, 31st with Dr. Stefan Manan. So just a heads up. Do you want to jump back to this one real quick?
Yeah. I mean, I guess that there probably more. Lots of people would have perhaps with some good illustrations, right? Because it's not that easy to visualize three-dimensional vectors inside a trajectory with the dog leg, right? But I mean, basically, what you look at the vectors, right? So there is a vector. So imagine that there is a piece of drill pipe between my hands, and the tension is pulling in these two directions. I mean, obviously they're not parallel because if you're going through a dog leg, they're not parallel. And then you can just take those two vectors and add them together. That means you get a new vector. It has a direction. So the magnitude of that vector, if that is bigger than the weight, basically, gravity times mass, then you know it will move. Right, so you use those two vectors, and then you can calculate where it moves, and it will be restricted by the circumference, the inner circumference of the hole. So it'll just move to one or other direction where it actually goes into sort of So basically, it's Newton's first law, right?
I could not have explained that, but yes, thank you for doing so. All right, Flora says, casing wear, do you take into account that the wear rate does not directly depend on contact force, but contact pressure, which changes when the wear groove propagates, even if the side force would stay constant? Florian asking the tough questions today.
Yeah, I'm trying to get my head around it. Contact force. I mean, And contact pressure, well, we're looking at the force divided by cross section, right? It's the pressure times the contact area. That's a force. So if maybe this is a little bit on the side of what they ask, because I'm not that 100% sure, but I mean, sometimes right, there are some, or in most cases, you combine a lot of operations, right, when you do a wear analysis, right? I mean, you have 8, 10, 12, 15 operations that you combine together, right? And all of them have been run with different types of equipment, different diameters, and if they do right, if they have been run with different diameter pipes and BHAs, the grooves obviously will be created in a way that they no longer at the end will represent one single sort of wear groove that you can say is part of something that had this or that diameter, right? It's like combine a lot of half moons lying into each other, and after a while it might look like it's still a half moon, right? But in reality it's not. And what's the actual radius of this? Well, it's certainly not the last stuff that we run down. That was 3-inch perhaps, because you started out with running stuff down with some 7-inch pipes, maybe 7-inch connectors, 8.5-inch connectors. Those cost, I mean, totally different grooves. You run down later on with smaller stuff, and of course different contact points, different movement, and you can try to calculate where things are actually located. Will it sort of fall into a groove when it starts to make a new groove? Well, I think in most cases it will, right? I mean, if you're lying on the edge of a groove and you apply a side force, a pressure, whatever you want to call it, so it will slide in and slide down to more or less its bottom, right, before it stops, and then that's where it will lie and increase the groove size, right?
Alrighty, so we got
If I understood.
yeah, I mean, there's a lot. I mean, it's probably one of those things where we're gonna all sit down in the same room and be able to talk that one through.
Yeah.
So we got a couple more questions here that we'll wrap it up. How much are the limits for collapse and burst rating reduction because of casing wear?
As far as I know, I'm not dug into the how it's actually used in real life. I mean, I thought that basically you would take the result from wear analysis to say. I mean, you derate the casings, right, with typically 12.5%. So it's 7.5 or what, if I remember correctly, on a general basis. And then if you have a wear result, then basically you can take that result, take those percentage, those wear grooves in a percentage value, and then insert that into your casing analysis, and then you get new numbers out, and you would see whether or not you could satisfy the government, right? Is this good enough for maintaining control of the well?
There you go. All right. Could you please recommend? This is from KF, not KFC, but KF. Could you please recommend a paper to get deep on torque in vertical wells?
Most papers that I've read is I mean, torque is just on a general basis. It's always in combination, right, with tension calculation. It's I mean, it's they're trying to get, you don't know what the tension is if you're rotating, if you don't know what the torque is, and vice versa, right? So you can't calculate one without the other, basically. And then, I mean, starting out with looking at the classical paper by Johansik, Dawson, and Friesen. That's a good starting point, right? You can see it's easy to search for where they've been referenced. You'll find a plethora of papers, I guess. I mean, look for the ones that have been written by the big theoreticians in drilling analysis. Yeah.
Here's Brendan Foster says, Florian and Truls, I think SPE 94300 is the concept you are talking about. It's an interesting idea that basically shows the crescent forms quickly initially, but then eventually reaches an equilibrium point where there is little wear based on the contact pressure threshold. Oops, that goes back to the previous question.
Yep.
So sorry about that. Cut you off on with the wrong stuff there. But hey, Brandon's watching. Thanks for watching, Brandon. Appreciate that. All right. One last question. I love that this is the last question. But how can we get a safe drilling parameters window to prevent or minimize wear in drill string? Because this is a very open-ended kind of there's a lot of I'm no torque and drag expert, but I know that there's a lot of answers to this one.
Oh yeah, definitely. I mean, no, I don't think there is Brandon talked a little bit about it yesterday, last week, right? I mean, sensitivity analysis, right? You want to sort of, when you do analysis, inserting a range of values instead of just inserting one and saying, I think it's on average is about this, and you insert that one, you do it, you get the results, and you look at it, it's okay. But I mean, sensitivity, so to be able to quickly play with a bunch of numbers, a range, to see what actually happens. So like sensitivity on the torque, right? No, not on the torque, on the rotation frequency, right? So we looked a little bit about that. Run an analysis where the rotation frequency actually is a range. What actually happens to the side for?
Oh. Did Truls freeze? Am I seeing this? Uh-oh. Hold on. Take him off screen real quick. Bring him back. Uh-oh. Well, that was the last question of the day. Truls, if you come back. Oh, there you are. Now he's back.
Oh, yeah.
Sorry.
I'll
let you finish real quick.
Continue. Yeah. No, so if you do sensitivity analysis, I think that would be my suggestion, right? Figure out the parameters you think are important, do the sensitivity, and then from that maybe you can do a much better choice on the final set of parameters, because basically you want to change more than one at a time. So sensitivity, I think, is a very good tool to figure out where you want to be.
All right. Well, Truls, thank you so much. Thank you to Oliasoft. Thank you to Friction Tool Solutions for sending me a disruptor. I mean, check this out. Oh, it's got a spider hanging off of it. There we go. All right. Thank you guys all so much for watching. Thank you so much once again to Friction Tools. If you guys have not, be sure to go over to their website. Check out the video they've got. This is some really, really, really interesting technology that they've got. They are a small company based out of Canada and are doing some really, really, really cool, interesting things in the torque and drag space and casing running. So be sure to go over there, give them a look. All right. I could not be happier with these guys. Once again, Truls, thank you. Thank you to Oliasoft. All right, guys, next week, we've got Dr. C coming on to talk about basic physics. That one's going to be brought to you by DTech. Low side torque and drag, cap stand effect, reaming vectors, and how the models work. All right, that's next week. The week after that, soft string versus stiff string models with Dr. Stefan. After that, Neil Armstrong from Merlin. That week that'll be brought to you by Cougar. Then Mitch with K&M over special operations. That one will be brought to you by WWT. And then we've got Devi who's going to be talking about operations and real-time torque and drag. That one's brought to you by D-Tech. And that would be covering drilling and survey practices, high angle hole cleaning systems approach, wellbore stability and loss circulation, tripping practices, real-time monitoring considerations, lot of operational stuff on that last one. And then once again, at the very, very end, we will be bringing back the one and only Mr. Brandon Foster to come back and be on the show once again. Truls, once again, thank you so much. Thank you for everybody out there watching. Thank you to Friction Tools. Be sure to go over there and check out their website. Go watch the video. Get in touch with those guys. Don't be shy about it. Like I said, Friction Tools. Thanks to David Dill. He's the one that won the drill bit. And that's it for me, guys. Be sure to like, share, subscribe, share this. Be back here next Tuesday, 8 a.m. for episode number 3. All right. That's it. Know your industry.